Okay, welcome back. So we are moving on to section 17.5, and actually we'll start on section 17.6 as well today because 17.5 is not too long. The title of this section is symmetries, and I want to mention that when a mathematician says symmetry, they don't necessarily mean exactly what we think naturally when we think of symmetry. We think of like mirror symmetry or rotational symmetry, and it's a generalization of that. A mathematician, when they use the term symmetry, they mean an operation which leaves a quantity unchanged. Okay, so a good example of that is your mirror symmetry, right? The quantity is what maybe you're viewing. It's the image that you receive. But maybe a less common example of a mathematical symmetry is something like conservation of energy, right? That's a physical law, and it says like no matter where energy ends up in a system, if I quantify the entire amount of energy, whatever operations the system is performing, the total quantity of energy remains unchanged. So that's maybe a less common example. When you're looking forward to your final projects, I know not all of you have signed up for these yet, but there's this theorem called Noether's theorem. In traditional American English, just say Noether. But Noether's theorem is a great example of how to find symmetries of physical laws. And so that's something to think of if you get interested in this idea of symmetries. You can sign up for that topic. And for this section, we're basically talking about symmetries as they relate to inner products. Okay, so in this section, we're saying the quantity which we want to remain unchanged is the inner product of two vectors. And you'll notice here in the first example, the vectors are functions, and our inner product, let's not forget that the inner product of two functions over some interval 0 to L is the product of those two functions, but the second one is taking a complex conjugate of, and then you integrate over the interval, which you can see directly above where that's written. That's a definition of the inner product, and it turns out that a symmetry in this sense is multiplication by e to the I theta, which is also, if you jump back to Euler's identity, or maybe your polar form of the complex plane, multiplication by e to the I theta is a rotation in the complex plane. So if I rotate my two functions phi and psi here, if I rotate them both by the same amount in the complex plane, and I compute their inner product, so there I've rotated them. If I compute the inner product, the adjoint, or I should call it the complex conjugate, you'll eventually see why I referred to that as the adjoint, but the complex conjugate comes down and it flips the sign on this exponential, which if I then move over via multiplication and use the exponential rules, the power of the exponential becomes 0 there. And so it's e to the 0, which happens to be 1. And so you notice that at the next line, we already recover our traditional inner product. So the inner product has remained unchanged under a rotation in the complex plane. And so what that describes is that multiplication by e to the I theta is a symmetry of, what is this space? The space is L2 of 0 to L. This is that L2 space that we like. So it's a symmetry of that space in the sense of it preserves the inner product. And something else we can talk about when we talk about symmetries with regards to inner products is this notion of a unitary operator. We're going to get into the definition and how to play around with operators in one chapter, basically. But what you can think about with a unitary operator is this is a generalization of a unitary matrix. And if you recall the unitary matrices, these were the matrices for which the transpose was equal to the inverse, if they're real valued. If they're complex valued, then you have to take what's called the Hermitian conjugate. But jumping back to perhaps what you've already encountered in linear algebra, the unitary matrices are the matrices whose transpose are their inverse. And an operator is just a generalization of that, because to transpose anything within a dot product, right? If I take something like x dot u y, this is equal to u transpose x dot y. And so if we generalize that in the inner product, the unitary operator would transpose as it moves to the left of the inner product. And in the case of unitary, if that transpose happens to be its inverse, then we recover u inverse u psi comma phi when we transpose. And of course, if that's the inverse, then we just recover psi and phi. So this is the generalization of unitary matrices to now my little L2 space, which has this different inner product on it, right? And so these are the symmetries of little L2. We call them unitary operators because these necessarily preserve the inner product. Okay, so let's see an example of another one of these. The matrix group O2, this is known as the orthogonal group in 2 dimensions. This is actually a subset of the unitary matrices because the orthogonal matrices are purely real, valued. And they can be referred to as either a reflection matrix or a product of 2 reflection matrices. So here's an example of like the set of reflection matrices. In particular, this one has a theta by it. Right, so I'm parameterizing this reflection matrix by theta, and it reflects a vector about the line passing through the origin with an angle of theta from the x-axis. So I mean, let's maybe be a little bit clearer about what that means. So let's take a line through the origin here with an angle of theta. Then what this matrix does is it grabs some vector. Let's make my vector out here. And recall matrices are just linear operations on vectors. So this matrix grabs the vector there and it reflects that vector over the line that I've given right here. And you could compute this if you wanted to. So this is ref theta. You could compute this if you wanted to and verify that, but that's the action of this reflection. And this happens to be an orthogonal matrix because what we seek out of, I should say unitary, right? Orthogonal is a subset of unitary. What we seek out of these matrices is that they preserve inner products. So actually, let's jump back here. You can imagine if I were computing the inner product maybe of this vector and this vector, so the cyan vector and the purple vector there, if I reflect the purple vector, make it blue when that one reflects, the purple vector kind of reflects here. And the inner product describes the angle between those two as well as their magnitudes. And you'll notice that the magnitudes of the 2 of them have not changed at all. And in fact, the angle of the 2 of them have not changed at all. So by preserving the angle and magnitude between 2 vectors, and really this should be any 2 vectors, we have unitarity. Okay, so those are the important things that we preserve, is the magnitude of vectors as well as their angles. That's what we need for unitarity, because the only thing an inner product will ever care about is an angle and a magnitude. Because of this notion, right? We have something like x vector times y vector. Inner product is the norm of the x vector, or the magnitude of the x vector, the magnitude of the y vector, cosine theta, where theta is the angle between them. And so you can see from this that if you preserve both magnitudes and the angle, then the inner product must be preserved as well. Okay, I'm going to jump down a little bit. And here we're now moving on to the next section. So that was just really a section saying these matrices, these operators exist in the infinite dimensional sense. We can think about one as the complex exponential multiplication. There are some others in the infinite dimensional setting. In the finite dimensional setting, we want to think about the matrices which preserve magnitudes and angles. So jumping down, next section, we're on bases now, which I know you're fairly familiar with, right? At least in finite dimensions, we have this lovely notion of, in finite dimensions, it's really easy to define our basis as 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, maybe in 3 dimensions. And we can write any vector as a sum of bases, and we can generalize that to any number of dimensions. But this next part is what's kind of important, and I would highly recommend that you jump back to the video that I shared from my other course, where I describe how we can think about actually Taylor series, which are functions which look like this, the Taylor series, as a basis. We can think about the monomials which construct the Taylor series as a basis for a function space. And this in particular, this setting is an infinite basis, right? These polynomials never end in degree. The degree marches up to infinity. And so this is kind of your classic infinite dimensional vector space, is the space of Taylor series. And the basis of that space is all of the monomials. But unfortunately, if you watch that other video of mine, this basis is not orthonormal, right? This basis does not have the property of being orthonormal because we don't actually have an inner product on this space. So if we want to be a little bit more clear about what it means to be orthonormal, the first thing we need to do is establish, this is in parentheses, bases in an inner product space for which the inner product of any two bases, I'm using En and Em, you don't have to worry about that, but I'm using En and Em for my two distinct bases, that's equal to 0 when distinct, if I can spell. Okay, so that's what you want to think about, is you need an inner product to talk about orthonormal for bases. And once you have that inner product, you need to guarantee that the I should say exponentials, the basis elements, when you consider an inner product between two of them, that those are equal to 0. Okay, this is what we need for an orthonormal basis. As well, since you can always gain a norm from an inner product. Recall this is the square root of the inner product of En with itself, that the norm is always equal to 1. So you really need this inner product space for orthonormality, where the first condition is that the inner product of two elements is 0. The second condition is that the norm of each element is 0. And what we're going to do here in the next example, this exercise, we will actually run through this, is for U, V, and W these are in R3, right? These form a basis, but not an orthonormal basis. We will often use the letters O and B to denote orthonormal basis. And so we'll jump over to the whiteboard to see why that might be the case. So recall U being 1, 1, 0, V was 1, 0, 1, and W was, actually I think V was 0, 1, 1, and W was 1, 0, 1. We can try out normality. This would be the normal part of orthonormal. And to calculate that, we just take U, which happens to be U dot U, square root. And if I compute that, U dot itself is 1 squared plus 1 squared plus 0 squared. I'm just taking each of the entries and squaring them and adding them together. I get root 2, which is not equal to 1. You would see the same occur for V, and you would see the same occur for W. Okay, so we're definitely not normal. Let's see if we're orthogonal at least. Something like U dot V to test orthogonality. If I take the dot product, I'm multiplying each of those, and I get 0 plus 1 plus 0, and that is very much not equal to 0. I can take U dot W, and that gives me I guess 1 plus 0 plus 0, which is not equal to 0. And then V dot W gives me 0, 0, and 1, which is still not equal to 0. So we're definitely not orthogonal either. And yet we are still a basis, right? I should at least show why we're a basis for these cases of U, V, W, 1, 0, 1. So let's show why we're a basis, because let's consider an arbitrary vector x1, x2, x3, and I'm going to make a claim that this is equal to x1 plus x2 minus x3 over 2 u vector plus negative x1 plus x2 plus x3 over 2 v vector plus x1 minus x2 plus x3 over 2 w vector. If this is true, right? We don't know this is true yet, but I'm making the claim this is true. And if this is true, then that's what it would mean for u, v, and w to be a basis, because it says that I can represent every vector in my space as a linear combination of u, v, and w. And so let's just verify that that's true really quick. So I'm gonna represent the right hand side as, well, x1 plus x2 minus x3 over 2 on u, because u has 1s in the first two entries, gives me x1 plus x2 minus x3 over 2, and then it gives me x1 plus x2 minus x3 over 2, and it gives me 0 in the third entry. V gives me 0 in the first entry and 1s in the next two, so I have negative x1 plus x2 plus x3 over 2, negative x1 plus x2 plus x3 over 2, and these are all added together, right? And then I do the same thing with w, which exists in the first and third entries. So I have a 0 here. Then x1 minus x2 plus x3 over 2 plus x1 minus x2 plus x3 over 2. And let's simplify this and see if we can get what we're actually looking for. I have a positive x1 over 2, positive x1 over 2. I have a negative x2 and negative x3 and positive x3. So what I end up with is precisely x1 over 2 plus x1 over 2, which is just x1. Here I have a positive x1, negative x1, so those cancel. Positive x2, so I get x2, negative x3, positive x3. And so those cancel. And then the same in the third case, my positive x3's add together, negative x1 and negative x2's cancel, and I get x3. And so there's a verification that, yes, indeed, this is a basis. It's just not orthonormal. So jumping back to the book, right, there's the exercise. Show that they form a basis and then show that they're not orthonormal. The remark is pretty nice. So orthogonal bases in finite dimensions will appear if we find the eigenvalues and eigenvectors for Hermitian matrices. Now, what does Hermitian mean? I'm not entirely sure if you all recall what a Hermitian matrix is. This is a matrix for which M transpose equals M. So a matrix, when you transpose it and it equals itself, that will give you an orthogonal basis, which is very useful. And then what we're jumping to next is this idea of maybe our inner product spaces have some sense of a natural decomposition into orthogonal components. So the question is this is what this is trying to say, do orthonormal bases exist in infinite dimension? We already saw that a basis exists in infinite dimension. That was the basis for the Taylor series. But the question becomes, do we have an orthonormal basis in infinite dimensions? And for that to happen, we need first an inner product space, and then secondly, we have to find an orthonormal basis. That's something that we'll talk about actually later. The answer is going to be yes, and we're going to see that come up in the next section. Anyway, that's all I have. I'll see you in class. Bye.